Okay, thanks a lot. Thanks again, Vincent. I think for the interest of time, I think we're going to take a very quick break. I suggest that we meet again in 5 minutes, it's 48. I suggest that we maybe, okay, let's save a 5-minute break, so we resume at 53. Okay? And with this, with Nicolas, and Nicolas, you can start already sharing from the LKB, very famous lab working on quantum systems, and who will talk about weakly interacting disordered Bose gases out of equilibrium. That was supposed to, okay, this is interacting. That was supposed to be, this talk was supposed to happen tomorrow. That's been switched with Jean-Claude Garot, and then thank you very much for switching the talk. Okay, you have the floor.
Okay, thank you very much for the introduction. So let me first of all join with the previous speakers to thank the organizers for setting up this nice workshop. And also especially for not giving up despite this difficult current situation. So yes, in this talk I would like to address the out of equilibrium dynamics of weakly interacting disordered Bose gases. And hopefully this will be a little bit a bridge between the physics that is discussed today and the physics that will be discussed tomorrow. So specifically in this presentation, I would like to try to show you that even in this relatively simple limit where the interactions are weak, the dynamics of a Bose gas may be quite non-trivial and reveal interesting effects. Okay. So before getting into the matter, let me simply say that most of this work has been actually done in collaboration with Dominique Delalande in our group, and also with Thibaut Skoka, who is our PhD student on this project, and he has actually a poster that you can see later in the afternoon. And many of the results I will present today were also obtained in with Cord Müller and Christian Miniatura in the early stages of the work, and more recently with Thomas Wellens and Pierre-Élie Larrey for the interaction part. Okay, so the general context of the talk, if you look a little bit beyond the physics of disorder, I would say is the out of equilibrium dynamics of isolated interacting quantum systems. So in this context, the usual configuration is the following. So initially you prepare your quantum system in, say, an eigenstate of some Hamiltonian. And then you quench it, namely you change a parameter of this Hamiltonian, and finally you just look how the isolated system is going to evolve unitarily under this change. So then with this protocol you can ask many questions, for example, how the system returns to equilibrium, what is of course this long-term equilibrium. You can ask, and this is the topic of the workshop, how the dynamics is affected by disorder, or in a different context, whether you have dynamical phase transition associated with critical values of the quench parameters. And as we've seen in the previous talks, nowadays this kind of questions is almost ideally implemented in cold atom settings. And the essential reason is that for cold atoms, with cold atoms, you can achieve the condition of an isolated system with very good accuracy. In addition, as you know, most of you know, with cold atoms, you can tune to a large extent the interactions, at least for certain atomic species. You can also tailor external potentials for the atoms, and in particular disordered potentials. And it's also relatively easy to perform time-resolved experiments. Okay, so here are a few more specific topics related to the quench dynamics of quantum gases, especially interacting quantum gases. So an old but still important question is the dynamical formation of Bose-Einstein condensates following a thermalization process by interactions. So it appears that nowadays, in fact, this question is quite popular beyond the field of quantum gases, and especially in optics, where people are trying to detect the dynamical formation of photonic BECs by implementing effective interactions between the photons. Now, if you just look at the thermalization, the dynamics of thermalization itself, this is a problem which is very much studied. In the recent years, in particular, it has been studied in non-integrable systems, which were shown to be described by approximate Gibbs ensembles even well before the full thermalization process is completed. And this is a mechanism called pre-thermalization, and I might come back to it a bit later. So it also happens in other systems that you quench, that the dynamics, again at short times, can exhibit universal self-similar scaling in its correlation functions. And this typically happens when you quench in the vicinity of a quantum phase transition or even through a quantum phase transition. Last but not least, there's the question of how strong disorder can affect the thermalization process itself and maybe even prevent thermalization, which is the case in the mechanism of many-body localization. And this will be extensively discussed tomorrow, in particular by Nicolas Cherroret. Okay, so in this talk, I would like to address a slightly different and somehow much simpler regime, namely the non-equilibrium dynamics of a Bose gas, which is both weakly disordered and weakly interacting. And if you wish, this is a regime where you are far from the many-body localization transition and where the interactions are essentially going to drive the system to a thermal state. And this will be probably called as the ergodic phase in the talks tomorrow. So to be more specific, in the rest of the talk, I will consider a very simple Quench protocol, which has been already introduced by Vincent before. So I assume that the Bose gas is initially prepared in a plane wave state, so a very simple state. And then that both a disordered potential and interactions are turned on together at initial time. And then with this configuration, I show you that non-trivial dynamics takes place in momentum space. And I will, in most of the talk, describe it with this disorder average momentum distribution. So since the gas is dilute, I will describe its dynamics on the basis of the Gross-Pitaevsky equation. So I remind you that this is essentially a mean field treatment of a Bose gas, where you have here this nonlinear potential that models the contact interactions between the particles. You have also this external potential V, which for my purpose will be a disordered potential. And what happens is that due to these two terms, the Bose gas experiences two types of scattering processes. So of course you have scattering from the disorder fluctuations, which typically change the direction of the momenta. But you have also particle-particle scattering or particle collisions in short, which additionally change the energy. So these two processes have different time scales in general. So disorder scattering is associated with the scattering mean free time, which depends on the microscopic properties of the disorder, and typically the mean disorder amplitude and the correlation length, sigma. And the particle collisions, on the other hand, are controlled by a certain particle collision time, which for contact interactions is essentially like this. So it's inversely proportional to the interaction energy squared of the Bose gas, G rho naught. So here rho naught is the mean gas density. And this density is here uniform because I remind you that we start from a plane wave, which is a uniform state in position. Okay, so before addressing the full scenario, let me start easily and first discuss the non-interacting limit at weak disorder. So this is essentially what has been explained in the previous talk. So here we neglect interaction. So we have just single particle physics in disorder. And at weak disorder, the theoretical description of the regime is very well known. So in short, it is based on the formal decomposition of a two-particle observable, like the momentum density, over all possible pairs of multiple scattering paths in the disorder. So in this decomposition, you have the diagonal terms here, which describe co-propagation of two scattering paths along an identical sequence of scattering events. And these terms are responsible for Boltzmann motion or diffusive evolution of the Bose gas. And then you have the interference terms here, which are responsible for localization phenomena. And as we've seen in Dominic's lecture, in the semi-classical limit, where the product of the gas momentum K0 and the mean-free path is much larger than 1, you can treat these interference corrections perturbatively. And this is the so-called weak localization perturbation expansion of the density. So let me illustrate what is observed in practice for the quenched plane wave. So again, at this stage, no interactions. This is what is shown here is the disorder average momentum distribution at two different times. So these plots are obtained by running the time-dependent Schrödinger equation in a 2D random potential. So at initial time, of course, you start from a plane wave, so it's a delta peak in the momentum space. And then after the disorder is turned on, after a few scattering time, this is what you get. So the distribution has been already discussed by Vincent. It has two essential features. The main one is this ring here, which is just the signature of classical diffusive motion. And this is formally described by this type of co-propagating sequences, which technically are called the series of ladder diagrams. And on the top of it, you see around minus K0 that you have a coherent backscattering peak, which is just the leading order, weak localization correction to the diffusive description. And it is obtained just by the interference between two time reverse scattering paths in the disorder. So now, if you also look closely over here, so in the vicinity of the forward direction, you see that there is also a smooth structure that slowly grows up in time. And this structure was studied now many years ago, and it was actually shown that it's due to higher order weak localization corrections. And an example of such correction is shown here. So this is a double loop diagram, which was actually identified very long ago in this classic paper by Hikami. So one can show that this diagram, due to the double loop structure, is indeed picked around the forward direction in momentum space. And as a small exercise, we can try to estimate its magnitude, which can be done by noting that the probability for this event to take place is essentially the probability for a single loop to cross itself again. And in the semi-classical limit we are considering here, the probability of self-crossing is just the ratio of the semi-classical volume of such a diffusive trajectory divided by the total volume accessible to the atoms. And the total volume accessible to the atoms in the diffusive regime is just dt. It's the law of diffusion in 2 dimensions. So then if you do the substitution, you get that the probability of this process in the diffusive regime is 1 over K0 L, so it's very small compared to 1. And this is what we see here, essentially in the numerics, the forward structure is very small. We can also try to extrapolate this formula to the localization regime, the strong localization regime, which in 2 dimensions takes place at long times. And in the regime of Anderson localization, the volume accessible to the particle becomes limited to the localization length square. And then again, if you do the substitution, you then get that the probability of the process over here grows in time in the localization regime, and actually the probability becomes on the order of 1 exactly at the localization time where Anderson localization is expected. So of course, this is here a very qualitative argument, but at least it suggests that this peak should be enhanced in the regime where Anderson localization takes place. So we can just look at the numerics, and this is indeed what happens. So the peaks, the forward peak here grows in time, and essentially the process stops when the full distribution has become symmetric and also completely time independent. So of course, if you want to now understand this long time structure, perturbation theory is definitely useless. But fortunately, there's another argument which is now based on the decomposition of the density over the basis of localized states. So the phi n's here are localized states in momentum space. And the point here is to notice that when you are at very long times, the phase factors over here oscillate, they vanish on average, and the distribution becomes essentially governed by the diagonal terms, which involve this average of the product of two eigenstate intensities in momentum space. So then you can use a simple result that these localized eigenfunctions in momentum space are actually Gaussian random variables, uncorrelated at different Ks. And this implies, by virtue of just the Wick theorem for Gaussian variables, that indeed the density, if you are exactly at plus and minus K naught, is exactly twice the density on the ring all around. So you see that this long time structure can be directly connected with the statistical properties of the localized states. So this is for 2D, this is for the long time limit. Of course, you can do much more. You can study the whole dynamics. You can also study what happens in other dimensions. Just as a remark, the three-dimensional problem has been also studied numerically a few years ago. And in 3 dimensions, it was shown, for example, that the forward peak only exists on the localized side of the Anderson transition. When you are on the diffusive side, the peak actually disappears at long times. I'd like also to point out that even though all this business is essentially numerical, there's a remarkable analytical prediction for the whole dynamics, which is available in quasi-1D. It was derived by Alex Atland and Tobias Miklitz a few years ago on the basis of the nonlinear sigma model. And it's interesting because this is actually one of the rare cases where you can completely solve analytically a time-dependent problem in disorder. So a few words about experiments. So as you have seen in Vincent Jo's talk, the dynamical formation of coherent backscattering was observed in his group with Alain Aspect in 2012. And more recently, they were also able to probe the control breakdown of CBS by change of time reversal symmetry. There was 2 years ago also a remarkable measurement of the coherent forward scattering peak I discussed before in realization, atomic realization of the kicked rotor and this will be discussed tomorrow. Okay, so now that we have the non-interacting limit in mind, let me add the particle collisions. So of course, from a theoretical point of view, now the problem is significantly more difficult to tackle, even though I would say we treat the interactions here at the mean field level. But nevertheless, the first relatively simple regime we can look at is what I call the mesoscopic regime here, where the mean free time is much smaller than the time scale for particle collisions. So this regime is simpler, at least from my point of view, because here, because the collision time is long, at short times, the dynamics remains essentially governed by disorder scattering. and the interactions, they only come afterwards, and they act as a slow perturbation of the picture. So what you see in this limit is shown here, and so at 3 different times, which are rather short, in fact. The essential difference with what I showed you before is that in the presence of interactions, the CBS peak now disappears as a function of time. And at the same time, you also have a slow deformation of the diffusive ring. So this effect is less visible here, but it becomes more and more prominent as time goes. So from a theoretical point of view, we can treat this regime rather easily because the collisions in this limit are much less frequent than the scattering events on the disorder. So in short, this means that you can treat the interaction just by inserting particle collision within the diffusive or weak localization or time reverse sequences of scattering events. It turned out that the contribution, the leading order interaction contribution that are relevant in this business are of order G squared, Gn squared. So what does it mean in practice? Well, if you look at the diffusive sequences, it means that in addition to the usual diffusive path, you have to account for the possibility that 2 particle collisions will interrupt a scattering sequence in between any 2 scattering events on the disorder. And you can have an arbitrary number of such processes along the trajectory. So if you have 2 particle collisions interrupting a scattering sequence, this can happen with 2 types of processes. Either the collisions affect a single path, here the black one, or they affect both paths at the same time. So however, it turns out that for the diffusive sequences where you do not have really interference mechanism coming into play, there's not that much difference between these 2 processes, and the net result of resumming all of them is just a Boltzmann-like kinetic equation for the diffusive part of the momentum distribution. And this Boltzmann kinetic equation essentially tells you that when you have interactions, the diffusive ring is no longer time-independent ring. In fact, it slowly washes out due to the interactions, which mix all the energies of the particles. And eventually, at very long time, the ring converges to a thermal distribution, which in the present context is the Rayleigh-Jeans distribution. So in a way, we here the quite natural result that weakly interacting, even disordered system is going to thermalize at very long time from a microscopic approach. And this is typically what people usually call the ergodic regime. So we can play the same game for the time-reversed trajectories responsible for weak localization. But now there's a fundamental difference. And the difference lies in this process 2, where I remind you that the 2 particle collisions affect both scattering paths of the sequence. So the point here is that because the 2 paths are traveled in opposite directions, now the locality, the time locality of the interactions imposes that these interaction collisions should occur at a very specific time, which is half the sequence. And this is by construction, but of course this is extremely unlikely. It's extremely unlikely that the collisions will occur only at this specific time. So this practice, this type of process is completely negligible for the dynamics, which is only governed by this type of mechanism. So we'll not go into the details here, but the consequence of this missing term is now that you have an asymmetry in the kinetic equations for the diffusive and weakly localized path. And in particular, the weak localization contribution to the momentum distribution now factorizes out of its collisional integral. So this means that if in a rough approximation, you say that this term does not change in time, you see that you just have an exponential decay of weak localization. So we have compared more quantitatively the predictions of this kinetic theory to exact Gross-Pitaevsky simulations. So this is shown here for the contrast of the CBS peak as a function of time. The theory is in black, solid curves, and you see that it compares well to the simulations for different values of the interaction strength. We have also found that the decay is well captured by an exponential relaxation with the decay rate of this process controlled precisely by the collision time I introduced before. Okay, so now everything I said so far works in what I call the mesoscopic regime, namely for very long collision times compared to the scattering time. So essentially in this regime, you have multiple scattering, you have mesoscopic effect like weak localization, and from time to time you have particle collisions that thermalize the whole thing. And incidentally, for the specialist, because in this regime, the interaction energy is typically the smallest energy scale, the thermalization process mainly involves particle-like excitations. So, of course, the situation becomes completely different in the opposite regime where, say, the collision time becomes smaller than the scattering mean free time. So now, because the disorder potential is much smaller than the interactions, if you wish, there's little and even no disorder scattering at all. So rather, we observe that the gas starts to behave more and more like a fluid. For example, in the regime where the velocity, the kinetic velocity is larger than the speed of sound, you see that you have a kind of supersonic, quasi-ballistic flow of the gas through the disorder. You have a little bit of scattering, and again, at long times, you have thermalization. Perhaps more interesting in what happens at low energy, in particular when the kinetic energy is smaller than the speed of sound, for example, 0. Here, it's not completely clear what happens if you just look at the momentum distribution, but we would naturally expect, because here the interaction energy is now the largest energy scale, we would expect a kind of superfluid behavior. So this is indeed the case, and let me briefly sketch how this limit can be tackled theoretically. So here we are at low energy. So the natural approach is hydrodynamical, namely you express the wave function of the Bose gas in a density phase representation, and then you use that the disorder potential is very shallow to linearize the Gross-Pitaevsky equation with respect to the density fluctuations. So this leads to the Bogoliubov-Dogen equations for intensity and phase fluctuations. These equations can be diagonalized, and then you indeed find that now the low energy excitations are phonons. And the interesting prediction here is that the variance of the phase difference between two different points in the gas increases logarithmically with the distance at sufficiently long times. And this logarithmic growth is really typical of interacting systems in 2D at low energy. It's actually a consequence of a more general theorem of statistical physics, which is the Mermin-Wagner theorem, which tells you that essentially in low dimensional systems, even tiny fluctuations are sufficient to destroy any long-range order. And most probably this kind of regime will be discussed more in detail tomorrow by Thierry Giamarchi in equilibrium systems. The practical consequence of this logarithmic growth of phase fluctuations is that the correlation of the field at two different points, which is just the Fourier transform of the momentum distribution, decays algebraically in space at sufficiently long times. And this is also what we observe in the numerics. In other words, this means that after an evolution in the disorder, in the presence of interactions, the Bose gas starts to behave as a quasi-condensate with universal algebraic correlations. Another interesting property is that this state is rather robust in the sense that it evolves very slowly in time. You have a small evolution, but this evolution is subleading, at least at short times, and this is related to a phenomenon that I outlined before, which is pre-thermalization, which means that the system is somehow stuck to this pre-thermal state for quite a long time. Just a last remark to show you that this behavior is completely different from what you have when you're dominated by scattering. When you're dominated by scattering, the regime I discussed in the beginning, you have multiple scattering, and therefore the spatial coherence of the Bose gas is very quickly completely lost. And in fact, in this regime, the spatial coherence is typically one mean free path, even less. So this is my summary. So I've showed you that the quench dynamics of disordered Bose gases in momentum space can be quite rich when you mix disorder and interactions, even at the mean field level. So we have essentially identified two regimes here. This mesoscopic regime where, in short, the interaction energy is smaller than the disorder. Then you have disorder scattering, you have weak localization, and interactions essentially dephase weak localization. So if there are condensed matter physicists in the audience, they will probably notice that this is exactly what happens for electrons, interacting electrons in conductors, which was shown by Altschuler many years ago. And you have on the other hand this opposite regime where the disorder is smaller, than the interactions. Here you have no disorder scattering, you have no mesoscopic effect. The gas behaves more like a fluid, and then you have all the effect that you usually see in low energy physics, algebraic coherence, pre-thermalization, and so on. In both cases, the fate of the Bose gas as long time is always a thermal state, which will involve particle collisions in this case and phonon collisions in the other case. And I'm done. Thank you for your attention.
Thank you, Nicolas, for this very interesting talk that is now open for questions. So if there are any questions, please raise your hands in the Zoom application. Okay, Thomas.
Yes, hi, Nicolas. Yeah, I have a question. You seem to emphasize that your treatment is mean field, which I understand well because you start from the Kospitevsky equation essentially. But then, how does it? I mean, when you treat the different diagrams and the fact that loops are broken, basically you invoke collisions, real collisions, like with momentum exchange. Which seems contradictory to me to mean field. So maybe I'm missing something here.
No, it's not contradictory. You can have an exchange of energies between the interactions even at the mean field level. So what the difference between mean field and not mean field, I would say, is that when you're not mean field, you have more possibility, so more, you have a larger number of particle scattering processes because you have, yes, you have more scattering, you have more interacting vertices, but of course you have also interactions at the mean field level with an energy change. Of course, the whole energy of the Bose gas at the mean field level is conserved, but you can have a mixture of the energies.
Sergey?
Yes, I would like to ask about the regime of strong scattering, because you mentioned on the left here, weak localization, Anderson localization. So it's not very intuitive that if I have Anderson localization and I add interactions that things will still thermalize. Can you comment on that?
Yeah, so this problem was actually studied before by, if I find the reference, yes. So this was actually studied, this problem, by a number of authors, but in particular by Denis Basco in 1D. So he considered the regime different from mine in a way where you have really localized modes. So he assumes that all the modes are localized and you have interactions between them. And if you work at the mean field level, then you come to the very same conclusion that the system thermalizes to a Rayleigh Jean distribution. What changes essentially is the collision time, so the time scale for reaching this thermal state. But of course here the question whether you treat the problem at the mean field level or at the many body level becomes important. And if you treat it at the many body level, at the mean field level, sorry, you find that there is thermalization. Actually, you describe only the ergodic regime of the complete many body level. At the many body level, this is different. You can have many body localization, and this will be discussed tomorrow, probably.
Okay, thank you.
Okay. Any other questions? So if not, I suggest we thank the speaker again. Thank you. Thank you very much. And I think the best thing is maybe to switch right now to the last speaker of the day.